Hi, everybody. My name is Deian Stefan. I'm an assistant professor at UC San Diego, and I work on computer security and programming languages. I'm at the intersection of these two areas. And today, what we're going to talk about is just basically a little bit about what computer security is and why I think it's a really cool area to do work in. So again, just to give you like a brief idea of like the kind of stuff that me and my group work on, we work at the intersection of computer security programming languages, and we kind of build systems to show that our work actually, the secure things that we actually do are something people can use in the real world. And what this means is sometimes I actually like spend time working with people in industry. I did this, for example, by finding a startup called Intrinsic that was now acquired by VMware, but I also spend time talking to people on working groups, right? Because like one of the things that we have to do as researchers is try to talk to people working on language designs and hopefully both bring new ideas and get ideas from them on like what are interesting and hard problems to solve. So let's talk a little bit about what computer security is. So what is computer security? Well, to answer this question, we're going to first look at what computer security is not, right? So if you look at most of computer science, it's really about functionality, right? So like if you look at architecture, operating systems, networks, databases, compilers, even programming languages, right? Like we talk about functionality, but when we look at computer security, it's really not at all about functionality. It's about how this functionality behaves in the presence of an adversary, right? Like we normally talk about compilers and build a compiler, but we don't talk about this compiler necessarily in the presence of, say, an adversary. Well, today what we're going to do is talk about these systems in the context of an adversarial setting. Um, so if we had to give computer security a definition, what would this be? Well, it would be something along the lines of it's the analysis and protection of computer systems in an adversarial setting, right? And we're going to break down all these different components, starting with what we mean by an adversary. So what is an adversary? Well, an adversary is someone who seeks essentially an outcome that's detrimental to your interest, or it's this adversary is trying to make your system misbehave in a way that gives them advantage in one way or another, right? And we can have different kinds of adversaries, starting from script kiddies, which are essentially just random people on the internet using tools that say hobbyist hackers have developed, and they try to like run these tools to just like mess with your systems or understand how systems work, right? And they might do this because they're curious. They might do it because they want to like gain fame. But as we kind of go from script kiddie to a specialist, right, the kind of abilities this person or this team might have grows pretty dramatically, right? And what kind of attacks they can carry out would be pretty dramatic. And this also like happens to go up with the motivation, right? So like we might start out with just curiosity or like fame, but there are definitely attackers who do it for personal gain, which might be, say, like stealing money. But there also might be attackers at the national interest level, right? So there are actually countries who have teams dedicated to cyber warfare, essentially. Okay. So now that we have a little bit of an idea of like what kind of adversary or what is an adversary, what we want to talk about is the second definition or the second word within this definition, which is like what do we actually mean by protection, right? So computer security is about the analysis and protection of computer systems. What do we mean by protection, right? So we have to actually say like what this means, and we're going to do this slightly formally, right? So we say that protection essentially comes down to one of three things. So one thing we might want from systems is we might want a system to give us confidentiality. What this essentially means is that we can't or we shouldn't be allowed to view protected information. Another property we may want from a system or the kind of protection that we may want is that of integrity, right? So what we want essentially is to a system to ensure that you can't modify information or the system itself unless you're actually authorized. And the last one that we typically talk about in the computer security field is availability, right? So we want to make sure that our system actually works as intended and provides access to proper users, but denies access to those who shouldn't be allowed to access these systems. And we want to, actually have systems that stay up even when somebody's trying to take them down. And we're going to go through all three of these in both the context of a physical world and computer systems. So let's start with confidentiality, right? So the goal of confidentiality is to prevent unauthorized access to private information, right? So what is a physical world example of this? Well, we have locks on doors, right? So locks on doors are a way of ensuring that only the right people could go inside the house. We have safes so that only the people who actually have the combination can look inside of whatever's stored within this safe, right? Okay, what about the um, uh, the cyber? Well, the two examples that come to mind are if you've used, say, Google Docs or uh, any of those kinds of online sharing programs, right? Like we create a document, and then one of the things that these programs let us do is actually restrict who can actually access this particular document, right? So by default, this document is totally private, but you can actually say designate it as anyone that has this particular link can actually read this information. And the goal of the underlying system that implements this document system is to restrict users to only those who actually have the secret URL. Another example is a browser. So, for example, the Tor browser is a particularly interesting browser because it's designed to exactly protect your privacy. And kind of as part of that, it has to ensure confidentiality. So, when you talk to a website with a Tor browser to actually load it, say, to like read news, one of the guarantees that we want is that of confidentiality, right? So, like nobody on the network should be able to see what website you're visiting and the contents of that particular website, right? So we want to make sure that you can browse the web in a way that's not revealed to, say, your ISP, right, or your school if you're at school. Okay, what about integrity? So confidentiality is one thing. The other one that we care about is integrity, right? So the idea of integrity, or systems that give us integrity, essentially prevent unauthorized modification of information. It could be the process or function or even the system itself, right? So we want to make sure that our system can't be tampered with, essentially, or data can't be tampered with or clobbered. So what are physical world examples of integrity? Well, one thing might be, say, a ballot box, right? So like one of the things that we want is to make sure that when we vote, that our ballots can't actually be changed, right? Or like when we sign a check, one of the things that we want, and the reason we have signatures, is to ensure that only the right person who is actually named on the check is giving the other person that receives the check the authorization to take the money out, right? So like we want to make sure that this is like a sense of essentially putting your own stamp on a particular document, saying that you're the one, and if anybody tampers with it, then you know that it's been messed with. Okay, what about on the in the computer world or the web? Well, two examples. Again, kind of going back to our confidentiality come to mind, right? So, for example, one thing that we have, or one thing that we want to make sure, is that the only person who can access my email or send email with my email address is me, right? And kind of like one way of ensuring that is by forcing me to type in a password and logging into Gmail with that password. The other one is the browser again, right? So like when we actually use, say, the Tor browser to talk to a website on the network, the other property that we want is that nobody on the network should be allowed to modify the contents between my browser and that server, right? Because one of the things that we want to make sure is that if I'm getting news, that news hasn't been modified, right? Because if it has been modified, then, well, A, I might be getting bad news, but B, and what an attacker can do is they can inject, say, code, and then my browser would run their code instead of the website that I originally intended to visit, right? So like it wouldn't be running the New York Times code, it'd be running the attacker's code, and that could lead to all kinds of nasty things. Okay, what about availability? Right. So the goal of availability is to prevent unauthorized denial of service. Right. So we want to make sure that our systems stay alive and can be used by the intended users. Right. So in the physical world, you might think of, say, parking lines that essentially are they're essentially a way of ensuring that we can use the parking lot in a most effective way, right? So in this particular case, we can fit 1, 2, 3, 4, 5, what is that, 10 cars. Whereas like if anybody parked in random order, that would be much harder to actually pack. And now this parking lot is no longer available to the intended users in the same way it would be with these lines. Right. Another one might be, say, one of these crosswalk signs that basically says when you should go or when you should stop. And this basically makes it possible for us to use our streets in a somewhat more effective way than if we just all walked whenever we decided we wanted to walk. Right. Okay. What about on the web or on the computer? What are examples of availability? Well, if you've used the Lyft app, for example, the Lyft app ensures that you can only order one car at a time, and this means that like not all the cars can be taken up by like one particular attacker, right? So I can't order 1,000 cars. That's pretty great because that means that they can service the other users and make sure that cars can actually pick up different users. Another example, if you hit this one, is the CAPTCHA, right? So the goal of CAPTCHA is basically a little puzzle that ensures that the only that only people can actually visit, let's say, your particular website. Or when you're logging in, you might hit these. And again, the reason websites have these is to ensure that it's actually human and not a robot trying to enter this particular website, right? And kind of the hypothesis here is that it's actually hard for the computer to actually, solve this particular challenge, but it should be easy enough for humans. Now, whether that's actually true is a separate story, but at least that's the intended goal of these CAPTCHAs. Okay, so now we kind of like have a sense of like what these systems are and the kind of three properties that they give us. What I want to look at is how these systems fails when we have adversaries come into play, right? So we have these systems that are designed to give us some properties, and we want to see how these fail when we have an attacker. So let's start with the last one, which is availability, right? So if we look at Lyft, well, Lyft is designed so that only that in such a way that only I can get one car, but not 1,000 cars, right? Well, it turns out that you can play dirty tricks, right? So if you look at an attacker, maybe not me personally, but an attacker that is, say, a competitor like Uber, well, they have thousands of drivers who they've convinced to actually order thousands of lifts and canceled those rides, right? So suddenly, when those thousands of cars were taken up, they were taken up by the attacker. And what that meant was that essentially those cars were not available to the actual users that wanted to use those cars, right? So this was essentially a denial of service attack carried out by Uber on Lyft. What about the CAPTCHA? How can we attack CAPTCHA? Well, again, if you remember, the goal of CAPTCHA is to make it hard for bots to actually get past this puzzle. Well, it turns out that there are actually services where you can upload CAPTCHA challenges and they'll solve it for you, right? And then that's one way to like completely bypass this thing, and suddenly like you can access this website when normally you would not be allowed to access the service. Okay, what about the physical world? Now that we've looked a little bit at the cyber world, where if we look back at our parking lot example, well, one way we can deny service is we don't have to park between those lines. There's nothing forcing us to. So we could just take up two spots. And in doing so, we've denied another car the ability to park in that particular spot. Traffic lights, same thing. We don't actually have to walk when it says walk. When it says don't walk, we can walk just as well. If we do this in a crowd, we're denying cars or pedestrians from the other side crossing, and as a result, essentially carrying out a denial of service attack, but in the physical world. Okay, what about integrity? Right. So in our integrity example, we had two things that we looked at. One was that only I can send emails with Deian@eng.ucsd.edu, and nobody can tamper with my connection from my browser Tor with whatever websites I decide to visit, right? Well, it turns out that databases get breached, and what attackers can do is they can go look up my password in one of these databases and potentially try to use that password to actually log in as me, and now they're able to not even force. They're able to pretend that they're actually Deian and send email with my email address. If you're a nation state attacker, like say Kazakhstan, you have the capability to intercept HTTP traffic, right? This is the encrypted and authenticated traffic between my browser and a particular website, right? And they've definitely done this, and they're not the only government to have done this. And in doing so, right, they're able to actually potentially violate the integrity that we would normally have of this channel between my browser and the remote website, and at least either temper it or identify me as a person, right? So this could violate confidentiality, as we'll see in 2 seconds as well. Okay, so let's get to confidentiality, right? So like, how can we violate confidentiality if we're an attacker? Well, if you give me one of these links, I can just put it on the internet. If I put it on the internet, now anybody has access to it, right? So this essentially, like this coarse-grained approach of saying like anybody who has the link can look at this, essentially trusts people to not share these links with attackers. But if somehow they do, or if an attacker is able to recover those links by, for example, getting you to download their extension, they can now get at information that they normally wouldn't be able to. And the same goes with the Tor browser, right? So like when you intercept traffic between my browser and a particular website, you not only violate integrity, but you could violate confidentiality as well. And within the browser case, one thing that I guess is relevant to both of these examples is when you install an extension, these are usually privileged pieces of code, and sometimes they're buggy, sometimes they're malicious, and they can get at information that you're viewing when you use the browser, and either deliberately or inadvertently leak this particular information, right? So like one thing it might be able to do is leak your secret Google Doc URL just because this thing wasn't written super well. Okay, so going a little bit more into this, like why are these things actually happening? Well, sometimes systems are poorly implemented, right? So a bug in your program, like saying your extension, may leak data. It might allow an unauthorized user to access particular data and affect critical operations of the system, so mess with the integrity of the system. But sometimes our assumptions are wrong, like even when systems are well designed. And our assumptions might go wrong in two particular ways. Like one, we might just have considered the wrong kind of attacker. So if we look at the real world, the attacker might be actually different from the attacker that we originally envisioned when we were designing the system. Or we just didn't consider how users may violate particular assumptions, like say keeping URLs secret. So let's look at this in a little bit more depth, starting with the physical world. So I want to start with physical locks, right? So physical locks are pretty interesting in how they work. They're actually kind of simple. So here I have two images of a lock that has been cut. This is from Matt Blaze and Stefan Savage. So the basic idea is the lock has a cylinder inside of it, and this is the inner cylinder, which you're also seeing here. Like the inside of it is what I'm coloring here, and that's the thing that actually rotates, right? Within the cylinder, what we have is this shear line that actually separates the cylinder, and we have the plug, which I call the cylinder. But the most interesting bit are the pins, right? So let me zoom in a little bit on these pins. Right, so we have top pins, and then we have also bottom pins that are below or above the shear line, right? So the top pins are above the shear line, the bottom pins are below the shear line. And what happens when we put in a key, as we have in the figure here, right? Like without the key, this example here, the pins are actually, blocking the shear line, and as a result, they're making it impossible for you to rotate the plug. But when we insert a key here, the bottom pins and top pins properly align, and now we have an opening so that we can actually rotate the key and rotate the plug, and that is how we open a lock. Right? Now, what are the assumptions of the system? Where the assumption is that we have a shared secret between the lock and the key, right? And it turns out this is actually a digital code, and it's called a binding code. What this basically means is that we can describe a key with a discrete code because we have the keys are cut at regular intervals. Usually you have between 4 to 6 cuts, which means 4 to 6 pins. And the depth of the cut is quantized, usually between 6 to 9 pins. And what this essentially means at the end of the day is that we can describe a key with 4 to 6 digits, right? So this key that I have here has different cuts. And if we look and analyze what these cuts are, well, they end up mapping to a number 64678, right? So we can just describe this particular key as 64678, and then you can tell a locksmith about this, and they can cut this exact key with with the right depth, right? So this has 1, 2, 3, 4, 5 pins, and the first pin is at 6, the second 4, 6, 7, 8. Right, and this, like, if you look at most of your house keys, they'll usually be 5-pin keys. Okay, so let's go back to our system assumptions, right? So we have a shared secret between the lock and the key, right? In particular, this digit. And for the system to actually work, we have several assumptions, right? So first, what we're making an assumption about is that if you don't know this secret code, you can't open the lock, right? So if you don't know that it's 64678, there's no way for you to actually turn the plug and open the lock. So that's assumption number 1. If we don't know the secret code, you can't open the lock. Assumption number 2 is that this secret code is actually secret, right? So like 64678 is actually secret, and you didn't tell people about it, right? And the third assumption is that, well, if we can't open the lock, then everything is all good. So let's see how we're actually going to violate all of these assumptions and how we can break into places that are protected by locks. So let's look at the first one, which is that if we don't know the secret code, we can't open the lock. Is this actually true? Well, it turns out it's not, right? So we can bypass locks by manipulating locks, right? So like, I have 2 examples here. First is that we can just pick and rake locks. So these are what lock picks actually look like. They're fun puzzles to take on the side if this is a thing you're interested in. The other way to open a lock is by using a bump key, which is the key on the right here. So let's look at a little bit of how picking locks actually works and how bumping keys lets you open doors. Okay, so how do lock picks work? Well, here's a diagram that basically shows the 2 things that we use when we pick locks. So the first is a tension wrench, which is this tool here. So this applies tension, in particular applies lateral force on the plug to essentially make it possible for us to bind the top pins above the shear line, right? So like, we use this to just slightly, sorry, my keyboard here is messing with it, just to apply a little bit of tension to twist the shear line here. And then that basically means that now the pins are all stuck the way you see it in this figure. And then we're going to use the pick, which is this second tool here, to lift each pin up just a little bit, right? And what we're going to try to do is we're going to lift each individual bottom pin up to the shear line, which ends up in a scenario where all the top pins are above the shear line, and now we can turn the plug. So if you haven't seen these before, I recommend looking at some YouTube videos or this how stuff works little video. It's really cool and it's really fun to do as a challenge. Okay, so we can use individual pins, and this is what the pin looks like in the real world. But we can be slightly lazier, so we can use other parts of our lockpicking toolset, like say a rake, which has a few more things. It's kind of hard to maybe show you in this figure. But the basic idea is, instead of being very precise the way we would with each pin, with raking, we're just going to move in and out quickly and force the bottom pins to essentially like add randomness and essentially lift the top pins above the shear line And doing this fast enough ends up actually working out pretty well. So like usually within 30 seconds, you can open most common household doors with just raking. And lockpicking is one way to do it. Another way to open a lock is using a bump key. So in this figure, we have a bump key, which is basically a key cut at all nines, so all the way down. And the idea is pretty similar to raking, where essentially we're introducing a bunch of random force and transfer of energy between the bottom pins and the top pins. So with a rake key, what you end up putting that in the lock, then you use a hammer to bump it. That ends up lifting all the bottom pins and pushes up the top pins just above the shear line. So with a little bit of tension, much the way we would do it with the tension tool, you'd be able to open a door pretty quickly. And again, there's just like lots of really great videos online for seeing bumping in action. Okay, so we just saw how not knowing the secret key is actually okay, because we can totally bypass this mechanism using either picks or bump keys to open a lock. Okay, let's look at how we may violate, say, the second assumption, which is that the secret code is actually secret. So if we think about this code being secret, well, what happens if I borrow your key, right? This is much like what happens if I tell you a URL. Well, I assume that you won't use, say, a tool like this that will essentially decode the key, right? So here we have field casting, which is basically just casting the key and creating a copy on the spot. Or you can just use a decoder, which will tell you the code of the key, and then you can just get one of these, go to one of these tools that duplicates or just makes keys given one of these blank keys and an actual code. It ends up producing a nice key replica for you, right? Okay, like how can we actually figure out like what the code is so that then we can use one of these tools? Well, borrowing works, but I don't even need to actually borrow your key to figure out what this secret code is. And to show you what I mean, well, one thing that people do is they take photos and put them up online, right? So here we have a photo on Flickr. Somebody posted house keys, right? Well, with a little bit of computer vision, we can rotate this image, add a little bit of contrast, and then actually figure out what the code is. So here the code is 53386. And if we actually look at it's a little hard, I guess, for you to see maybe. Let me try it better. If we look at the number here, you can kind of see that it's actually saying the same thing, which is 53386. Right? So sometimes like the key is just written there, but you can also figure out what the key actually is, or the code is, just by doing a little bit of measurement digitally. Okay. So we can identify keys like this, but like you're not always going to post your keys online, right? Like this is something, at least from now on, that I hope you don't do. Still, if we think about our attacker model chart, right? Like we may have attackers that are not, say, script kiddies, but are actually specialists, and they're motivated by national interest, right? So we're talking essentially about spies, right? So if you're a spy, what can you do? Well, you can do what my colleagues at UCSD did, which is something pretty awesome. So here we have an image that was taken from the roof of our building. And on this table here are a set of keys, right? So the challenge that they wanted to undertake was, well, if I'm this far away from you, can I somehow still figure out what the secret code of a particular key is? So how do you do this? Well, they got a telescope and a camera and zoomed in on those keys. They got a nice photo of the keys, then used some computer vision techniques to figure out that the key combination here was 74753, right? So if you're a pretty sophisticated attacker, you can do these kinds of things. And that's kind of like pretty awesome and pretty scary at the same time. Okay, so now we know that if we're relying on the secret code to be secret, that may not necessarily be true when we think about attackers. Okay, so let's look at our last assumption, which is that, well, if we don't, or if we can't open the lock, and in particular, what that might mean is like we can't figure out what the secret code is, or we can't pick locks because we're just not that kind of attacker. So we're not a very good lock picker. We're also not very good at machine learning or computer vision to actually take a photo and figure out what the secret code is. Can we still somehow get inside? Well, yeah, right. So like one thing we can do is we can just break the door, enter through a window, or break a glass, right? So like it's not the case that you need to that if we don't have the lock, or that the lock won't actually give us the guarantees that we want. Okay, so what's going on again, right? So sometimes our assumptions are wrong, and it's not the case that these systems are poorly implemented. Like locks are perfectly fine, but we didn't consider certain kinds of attackers, right? Like somebody that might break through a window, somebody that might be able to pick locks, or somebody who might be able to take photos from a far distance and recover the key, the secret code of the particular key. Okay, so what's the equivalent online? Well, passwords are pretty close, right? So with passwords, we have essentially three assumptions, right? That if we don't know the secret password, you can't log into my Gmail account, and that the password is actually secret. And finally, if you can't log in, then everything is fine. And here, what I mean is you can't read my email, or you can't send email under my email address, right? Well, how would these things be violated in the non-physical world? Well, let's see. Let's look at each one in turn. So, okay, if we don't know the secret password, then we can't log in, right? So how could this assumption be violated? Well, one thing we could do is, as the attacker, we can repeatedly try to guess passwords, right? So this is kind of hard to do for Gmail accounts, because Google's actually pretty good about this. But like your home machine might be less good, and there are pretty good password cracking programs out there that would be able to actually cover many common passwords. Right, so they're pretty clever about putting leet speak, like ones and threes and zeros at the end of passwords and things like that. Okay, so password crackers are a way to violate this assumption. What's the other one? Well, that the password is secret, right? So we're making an assumption that the password is indeed secret. What happens in the real world? Well, users turns out to reuse passwords, and then websites where you use these passwords get breached, right? So these websites get hacked, and these attackers sometimes post all the credentials in particular databases. As an attacker now, I go to one of these databases, I look up your email address and your password and try that password to many other accounts. This turns out to work really, really well, right? We're really bad about reusing passwords, and we should completely stop doing that. And just, if you're going to take anything from this lecture, is you should use a password manager. You should not try to be clever about coming up with your own passwords, and you should definitely not reuse passwords. Password managers really help you with both of these issues. Okay, but suppose my password is secret. Is it the case that if I can't log in, then everything is fine? Well, not really, right? So like one thing, as an attacker, I may not try to brute force your password, right? So I may not try to guess it. I may not even look at these databases, because maybe you're pretty good about your passwords. A thing I might do is convince you to install an extension that I wrote, or that somebody else wrote and I bought from them. And this extension will then just go ahead and steal personal information from the sites that you visit where this extension is actually running. Right? Or it doesn't have to be even this sophisticated. Extensions have bugs, and if I, as an attacker, can convince you to visit my website, I could potentially exploit this extension and then take advantage of this extension's privileges to look and find your passwords for different websites. Okay, so this kind of fits into the first category of what's actually going wrong or what's going on, where systems might be poorly implemented, and as attackers, we might be able to take advantage of these things. Okay, so why are we so bad at this? Right, if you've looked at news, you've probably seen that websites keep getting breached. There's security nightmares all over the place. Well, the reason this is happening is manifold, but like one of the reasons is that building secure systems is actually super hard, right? So the attack surface is huge. And to show you what I mean by this, let's look at one website. If you're, say, a blog organization or just trying to run your own blog in a way that modern websites do. So like one thing we may have is we might have a server that users connect to when they want to load up blog.org in their browser. This blog.org web server might talk to a database server to get and store data, right? So now we have at least two servers, and we have some code running in the browser. Okay, so where's the attacker? Like, how do we think about this? What is the attack surface? Well, the attacker could just be somebody on the network trying to talk to our web server. The attacker can also try to just talk to the database server directly. They might also be in the browser, right? Like users visit malicious websites pretty much daily. So the attacker could be in your browser. The browser does actually isolate, different websites like blog.org would be separated from evil.site, but the attacker might still try to take advantage of bugs in the browser to then compromise your code running in the browser here, right? Okay, so the attacker can be on all these different interfaces. They may even be, in an extension, right? Like I mentioned extensions quite a few times. The attacker might be either malicious an extension, or they might be an evil website trying to compromise a buggy extension and essentially take over the extension to do whatever they actually want to do. It might even be trickier than that. They may even be in your web page, right? Because they might be injecting code as a third-party library, right? So they could have backdoored a library. They could have compromised a library author's machine. If you depend on this library when you're building this system, they can run in the browser. They can also run server-side, right? Like whenever we build these systems, we build them using libraries written by third-party developers, right? Like modern websites are super complicated. And we rely on lots of third-party code. If I can compromise any of those things, well, now suddenly I get the capabilities of either your web server or the client-side code running in the browser. All right, so this is a lot to worry about, and we're not all going to be thinking about this when we're building functionality, right? It's pretty hard to do, even if we were security conscious, this is a really, really hard thing to do. And to convince you, I want to show you like why, right? So like one of the reasons is when we're building systems, we're using general purpose languages, and these general purpose languages are typically not designed with security in mind. So many languages are actually unsafe by design. And one of the most popular examples of this is the C and C++ languages. So just to give you kind of a flavor of how things can go wrong, I have here a very simple program that has three functions. So the main function is the thing that we're going to run to start. And all this thing does is it calls say hello with the first argument that I pass to the program. And what does say hello do? Well, say hello has a local buffer that just starts with hello and space. And then what we do is we concatenate whatever that argument we pass to say hello to this buffer here, and then we print it out, right? So if we run this program with, say, hello, Deian, it's just going to print out to the terminal, hello, Deian. Now you'll note that this program doesn't actually ever call this function by, right? But there is a bug in this program, and maybe like if you haven't written lots of C code, you wouldn't notice what this bug is or why this would appear. So like to start, you'll note here that hello has length 16. So if we give it a long name, well, we're going to get past the length of this thing. So if we say give it down and then just keep going, we're going to write beyond this 16-byte boundary, right? So if we do that, what happens? Well, it's going to print out hello and whatever I gave it, but it's also going to crash, right? So, okay, maybe crashing is okay because we wrote past this buffer, the length of this buffer. And this is what you're going to see with many other languages beyond C, where like if we try to write past the length of a buffer, the program may crash. But what's interesting about C is that we can maybe do something worse as an attacker, right? So here as the attacker, I supply input to this program. So one of the things I may try to supply is this string that I came up with earlier today. So I'll first just print it for you. So I'm using Python to print out what the string is, and this is a string that we're going to feed to the program. So this is just a string with a few weird characters at the end, right? So if I now run this example with that string as the argument, what happens? Well, I'm able to actually execute the by function, and I got your program to execute code that it normally wouldn't have. Right? At least like when we look at the normal functional behavior of the program, it should never call the by function. Yet by supplying it clever attacker input, we're able to divert its control flow to other parts of the program code that it never intended to execute. And we can do all kinds of interesting things when we hijack the control flow of a program. Right? So, okay, maybe what you're going to say is like, well, okay, we shouldn't be using these languages, and you definitely shouldn't, right? Like if you're building new systems, you should avoid these unsafe languages and write in higher level languages that don't have these classes of bugs. But even in those languages, you have to think about security because there are different attacker models that you have to worry about. In particular, like even high level languages like Python, they don't have any abstraction for security or privacy. So for example, if you wanted to implement a web server or a web application, how would you go about saying that, like, if checking whether or not this particular user that you're running this piece of code on behalf of is allowed to access any particular data or perform certain pieces of action? Well, you're going to sprinkle if statements. That's basically what ends up happening today because we don't have better abstractions for doing this, right? So what does that mean? Well, it means that your code base ends up looking something like this. So this is a piece of code that is hopefully blurry to you, and what the code actually does doesn't really matter. It's just the shape of the code more than anything else that actually matters. And moreover, what this code, where these arrows are, this code is actually sprinkling those if statements that check whether or not you're allowed to perform a particular action. So these are the lines of code that actually perform security critical checks, right? Now it's really scary because if we miss any of these checks, that means we have a security vulnerability and potentially an attacker can either steal information or corrupt information from this particular website, right? So like this is a really, really bad way to try to build systems because we're definitely going to miss these checks. There's nothing stopping us from writing code that ensures that these checks are in place. Okay, so the programming languages don't actually help us. Even if they did, when we build large systems, we do so by taking a bunch of different components and putting them together, right? So if we think about the earlier example that I had, which is running a blog application, we're going to have our HTTP front-end web server, then we're going to have our database system. Well, these two systems have different attacker models, right? So database systems happily execute any query you give it because they don't assume that the queries that you give it are actually attacker supplied. But when we glue a database system with a web server, well, suddenly the web server handles untrusted input because anybody on the internet can send a request to your web server. And if your web server just sends this query directly to the database, what happens? Well, now suddenly the query is untrusted and it can perform whatever actions the attacker wanted. In particular, it could drop all your tables and remove everybody from your database system, right? And this actually still happens, right? These aren't just examples that I'm making up because they're interesting to talk about for a mini lecture like this, but they're actual things that still happen to modern web apps. Okay, the last reason we're really bad at security is as kind of system builders, we think about security after the fact, right? And this has been largely a culture problem, and kind of it's percolated by huge companies to some degree, right? So it's easier and still cheap enough to deal with security problems after the fact, right? Like if you're Facebook, well, you can probably pay out quite a bit when you have huge security problems. But this, like, if you look at especially recent news, this is a really bad idea, because we have, say, hospitals that are getting compromised, and their databases are getting encrypted by attackers and used as ransom. Um, and what this means is that doctors now don't have access to these systems. They don't have access to this data, which means that people's lives are actually put at risk. It's not just money. This is actually affecting real people, and potentially leading to deaths that could have been prevented otherwise. The other reason is because there is this notion that security costs, like there's a trade-off between security and something else. And that something else is usually performance or, say, features, right? So, if we try to build a more secure thing, what that might mean is that we now have to have a slower system, or we might make it harder for developers to actually build things if they had to deal with security. So there's this trade-off that we think is inherent. I want to actually tell you that it's actually not. We just need to spend more time building tools, and I'll talk a little bit about that in a few slides. Finally, security is hard to measure, right? So, like, unlike performance, where you can put a timer between, say, a function call or RPC message, with security, it's really hard to say, like, this is giving you this much security, right? Or whereas with, and same goes with features, right? Like, when you have a new feature, you don't necessarily know very easily if you've gotten that much for the security mechanism that you try to use. But it's not all doom and gloom, right? We actually know how to build secure systems, and kind of my group's approach has been to essentially do this by minimizing the amount of code that we need to trust. So if we're looking at how we build large systems, well, these systems have lots of third-party libraries, like I mentioned before, and today these libraries are completely trusted, which means that if there's a bug in a library, your whole application can be compromised, right? So what we've done is we've developed this framework called RLBox that essentially puts, say, whatever library you may have, which is just one bit of your application, into a sandbox, right? So this is in a separate world from your application, and we have nice interfaces between your sandbox library and the rest of the application. So what we get at the end of the day is basically, if there is a bug in with this library, it can't actually compromise the application. At worst, what the library, when compromised, would be able to do is, clobber the library sandbox, but it can't get at important application information, right? So by splitting out, huge applications into these sandbox libraries, we're able to build applications that have way less code that we need to trust. And what that means at the end of the day is, like, way less code that could have potential security implications. Right, and this is like actually research that has led to adoption in industry, and one example of that is the Firefox browser. So if you're using the Firefox browser, which I totally think you should, they actually use the sandboxing framework that we developed. In fact, we developed it with folks at Mozilla to exactly sandbox third-party libraries in the Firefox browser. And what that basically means is that if you're visiting a website that may have, say, malicious content, this malicious content can't exploit a bug in a library, or at least the ones we sandbox, to compromise the rest of your browser, which could then be used to compromise the rest of your system. But okay, this is just like one example of directions directions towards more secure systems. There are other ways and more work that we need to do. So, for example, we need to develop new tools and new languages that can make this easier. We also need to actually change the culture around security, right? So it seems like we're already witnessing that the new generation of engineers, which I hope many of you will take this and run with even more, are starting to think about security from the start and building secure systems, or at least systems with security in mind from the start. And finally, we have regulation, right? So, like, not everything can be solved with technology. We need new regulations and new laws that are actually going to help prioritize security and privacy. And those seem to be actually, at least in Europe and in California, be taken more seriously. Okay, so with that in mind, I would like to thank you for listening in, and You can find my contact information online if you want to chat about anything security. Thanks so much.